So today we're going to be learning about nodal analysis. Um, this is a very powerful circuit analysis tool in which we apply Kirchhoff's current law multiple times in order to solve for every unknown voltage in our system. Okay. So we're going to learn nodal analysis and the step-by-step algorithmic approach by practicing with specific problems. Okay. So the first problem that we're going to look at is this guy right here. So we're going to start off our nodal analysis with circuits that only contain current sources. We're going to figure out how these work, and then we are going to adapt this method to be able to handle what happens when a voltage source is present in the circuit as well. Okay. So let me go ahead and label some of these things really quickly. So let's say that this is a 5 ohm resistor. Over here might be a 10 ohm. Let's say that this is a 20 ohm. This is a 25 ohm. Let's make this a 2 amp current source. And let's make this a, let's see, 3ix current source actually. Let me use capital I since this is a DC circuit, where I'm going to say that the current Ix is this current right here. So this is a circuit that we're trying to analyze, and I think it looks relatively gross. Okay. There are no simplifications that we can make because there are no resistors that are connected in series or in parallel. There are no sources that are connected in parallel. So we just have this gross looking thing. So this is how we're going to start nodal analysis. So our first step in nodal analysis is simply going to be to identify our nodes. So I'm going to do that the exact same way that I've done it every other time in this class by just starting with different colors and labeling things like so. Okay. So we've got one node here on the top, a node here on the left-hand side, a node here in the middle, and lastly, we're going to have a node here on bottom. So step one has been completed. Okay, so that one's fairly easy. Step number two is going to be to assign a reference or ground node. Okay. So I'm going to use the terms reference and ground interchangeably because in this context, they mean the same thing. So by assigning a reference node, what I'm doing is I'm saying one particular node in the circuit has a voltage of 0, and that's the one that I'm going to measure every other voltage against. Okay. So typically speaking, in a circuit like this where there aren't any voltage sources, so we only have elements and current sources, I would assign the ground or reference node at whichever node is touching the largest number of elements. But we can see that the red node touches three elements, the green node touches three elements, the blue node touches three elements, and the purple node touches three elements, which means every single node in this circuit is as equally good of a one to choose as your reference node. So I'm going to allow you guys to just tell me which one the reference node is going to be. The bottom one. Okay. So I'm going to denote the reference node by putting a ground symbol here. Okay. Okay. Now we have step number 3, and this is going to be to assign nodal voltages to all non-reference nodes. So I'm going to call this node on top node A, and I'm going to say that there's some nodal voltage VA present at this node, and I'll explain what a nodal voltage is here in a moment. I'm going to say that the green node on the left is node B, so I'll have some nodal voltage VB. And lastly, this blue node is going to be node C, so I'll assign this guy a nodal voltage VC. So now let's talk a little bit about what a nodal voltage is, okay? So the nodal voltages, as I've assigned them, is just a shorthand way of writing the double subscript notation where the letter A, or for node A, is going to be the positive polarity terminal of voltage VA, and ground is going to be the negative polarity terminal. So another way to think about nodal voltage VA would be this voltage drop right here, which would be the voltage drop across that dependent current source because it's connected between node A and ground. Very similarly, the nodal voltage VC would be the voltage drop across this 20 ohm resistor, VB, because the 20 ohm resistor is placed between node B and ground, and the voltage drop across our 25 ohm resistor would be the same thing as our nodal voltage VC because it's placed between node C and ground, okay? So a nodal voltage is just the positive polarity terminal is assumed to be at the node that's labeled, and then the negative polarity terminal is always ground, okay? So I'm going to erase these resistor voltages and stuff like this because we no longer need them. That information is conveyed by those nodal voltages. All right, so step 4 is technically going to be an optional step. And what I mean by that is if we don't have any dependent sources, then we can skip step 4, okay? So step number 4 is going to be to express our controlling variables in terms of the nodal voltages. So in this case, our controlling variable is the current Ix that's defined as flowing down through the 10 ohm resistor because that current Ix is controlling that dependent source on the right-hand side, okay? So what I'm going to do is I'm going to write a KVL equation and then rearrange it. And we're going to see if we can glean how this works so that we can do it in a faster way in every subsequent iteration of this, okay? So perhaps I shouldn't have erased those things. So I'm going to wind up putting them back in here. So we know that this voltage is VC because it's measured, the positive polarity terminal is at node C, the negative polarity terminal is at ground. This voltage right here is VA, like so, because it's between node A and ground. And I'm going to call this voltage across the 10 ohm resistor. Let me just put it in this. V10, like so. Okay. So I'm going to do this over here on the left-hand side of the page. So I can see, I believe pretty easily, that if I do KVL around the right-hand side of the circuit, I would get the relationship negative VC plus, minus V10 plus VA is equal to 0, which I could then rearrange to say that the voltage V10, so the voltage drop across the 10 ohm resistor, positive polarity on top, is just going to be VA minus VC. Are we all okay with that? Okay. So now using Ohm's law, I could say that our controlling variable Ix is just the voltage drop across the 10 ohm resistor, which is VA minus VC, divided by 10 ohms, which is the resistance of the resistor we're finding the current through. Okay. So this was a long way to get this result. Now let's talk and see if we can figure out a shorter way to do it. Okay. So whenever we're writing these current expressions, we're always just applying Ohm's law. Okay. So how I like to think about it to do this faster is I typically say, well, what node is the current starting from? So it's starting from VA and it's flowing towards VC. So that means I'm going to have VA minus VC in my numerator. So the node where it starts minus the node it's flowing to divided by the resistor value is going to give us the exact same results as doing that KVL and then Ohm's law in a subsequent step. So this is how I'm going to do it faster from here on out and how I suggest you guys do it as well. Okay. So this is our only controlling variable. So we are good to move on to step number 4. Actually, let me pause here and see if anybody has any questions. Yes.
You just said about the shorthand thing?
Yeah. So this current is flowing down through the 10 ohm resistor, right? So what node is it starting from? What node is it flowing to? Okay, so that's why I have VA minus VC. And then I divide by the resistor value because it's just the voltage drop across the element divided by the resistor gives us current because that's literally just Ohm's law. I is equal to V over R. Yep.
So if we have a 5 like resistor 25, that just be VC over 25?
Yeah. We'll do that in literally just a minute. Yeah. So 100% correct there. All right. So step number 5. We are going to apply Kirchhoff's current law at each non-reference node. So in this case, we have 3 non-reference nodes, so we're going to have to write 3 KCL equations, okay? So I'm going to start with KCL at node A. And I'm going to draw some arrows here to help us figure out what to do, okay? So I'm going to apply KCL number 3, which means the currents that are leaving the node of interest are going to add together to make 0. So that means I'm going to be adding this current flowing down through the 5 ohm resistor, plus this current flowing down through the 10 ohm resistor, plus this current flowing down through the dependent source together, okay? And setting them equal to 0. If at all possible, I'm going to put all of those terms in terms of my nodal voltages, okay? So applying KCL at this top node VA, what's the current that's flowing down through the 5 ohm resistor going to be based on the methodology that we've established? So VA minus VB over 5 ohms, okay? What's the current flowing down through the 10 ohm resistor?
VA minus
Yep, VA minus VC over 10. And lastly, we have the current flowing down through the dependent source. And for what it's worth here, because there's a current source here, we can't do this in terms of nodal voltages because we are being told what that current is. Any thoughts? 3ix. So if the current source tells us that there's 3ix of current flowing down, then that's how much current there is.
Can't you put, VA minus VC over 10? Like that 8 times.
So VA minus VC over 10 is the current that's flowing down through that 10 ohm resistor. This guy is a different current. Now, are you saying multiply that by 3? So we could do that as a substitution, and we probably will wind up doing that in a minute. But whenever I see a current source, I just put the magnitude in the equation. Okay. So now we're going to do KCL at node B. So at node B, we're going to have this current flowing up, this current flowing to the right, and this current flowing down. So let's start with the current flowing up through the 5 ohm resistor. What's that going to be? VB minus VA, that's a voltage, over 5. What's the current flowing to the right through that current source? Negative 2 amps. So the arrow that we're following is in the opposite direction of the arrow of the current source, so we need to change the sign. Okay. And then what's the current flowing down through the 20 ohm resistor? VB minus 0, so just VB over 20 ohms. Lastly, we'll do KCL at node C. So that'll be this current, and this current added together. So what's the current flowing up through the 10 ohm resistor? VC minus VA is a voltage over 10. What's the current flowing to the left through the current source? Positive 2 amps, because that arrow in blue is in the same direction as the current source. And lastly, the current flowing down through the 25 ohm resistor. VC over 25. So we currently have 4 equations and 4 unknowns, right? So here's our first equation from our controlling variable relationship, and then our second, third, and fourth equations from our KCL relationships. So if we have 4 equations and 4 unknown quantities, we should be good to go to throw this into a system solver. Now, if you have a TI 36X or a Casio 115, it can only do a 3 equation, 3 unknown system. The Casio 991s can do a 4 equation, 4 unknown system, okay? So if you've got the 991, you could stop here and just go on about your day. But because I got my 36 out and I'm going to do it on the virtual calculator so I can show you guys, I'm going to have to make a substitution. And I'm going to make the exact substitution that was suggested earlier, where I see IX, I can just replace it with VA minus VC over 10, giving me a 3 equation, 3 unknown system, okay? So I'm just going to scratch this guy out right here and replace that with 3 VA minus 3 VC over 10 ohms, because that would be the same thing as 3IX. All right, let me open up my digital calculator here. So, bless you. I'm gonna clear my memory and we're gonna go into the system solver by pressing second and then tangent. And now we're solving a 3 by 3 linear system of equations. So I'm going to do option 2. Okay. And so in the first column, I'm going to put the coefficients for VA. In the second column, I'm going to put the coefficients for VB. In the third column, I'm going to put the coefficients for VC. And in the fourth column, I'm going to put any constant terms I may have. Okay. So in this first column, first row, first column, I can see the coefficient of VA is going to be 1/5 from this leftmost term, 1/10 from the middle term, and 3/10 from the right term. So I'm just going to put in 1/5 plus 1/10 plus 3/10 and press enter. I'm going to let the calculator do the math for me because I'm too damn lazy to do least common denominators and add all that shit together. It's not worth my time. Okay. So what's the coefficient for VB in this first KCL equation? Negative 1/5. So I'm just going to do negative 1/5. Okay. What's the coefficient for VC? So there's negative 1/10 from the middle term and negative 3/10 from the right term. So I need to include both of them. All right. And I don't have any constant terms, so I'm just going to leave that as 0 and press enter. Now I'm on to my second equation. Okay. So we're now at the KCL at node B equation. So what's the coefficient for VA in this guy? Negative 1/5. What's the coefficient for VB? Yep, 1/5 plus 1/20. What's the coefficient for VC? 0. And the constant term will be positive 2 because I need to move it to the other side of the equal sign. So you guys that said 2 were correct. Now we're down to our KCL at node C equation. So what's our coefficient for VA? Oops, I must have typed that in poorly. My coefficient for VB is 0 because there aren't any VB terms here. My coefficient for VC, 1/10 plus 1/25. My constant term here is going to be negative 2 when I move that 2 amps over to the right-hand side of the equal sign. And so I'm going to go ahead and down here write step 6, which is just to solve our system of equations. And according to my calculator here, VA is negative 80 over 3 volts. VB will be negative 40 over 3 volts. And lastly, VC will be negative 100 over 3 volts. So before we move on from here, did anybody else get these same results when they put it in their calculator? Got a couple of people nodding their heads, raising their hands, all that kind of stuff. All right, good deal. Okay, so we have learned how to apply the nodal analysis technique to solve for these voltages, okay? So what if we were interested in something else, okay? So what if I wanted to know the power supplied by that dependent source. So I'm going to write P sup dependent here. Okay. Anybody have any thoughts on how we might use the results of our nodal analysis to determine this?
What is IX equation?
Okay, so we know that there's 3Ix of current in our system. Okay, so we're going to have 3 times VA minus VC over 10 ohms. All right. What's the voltage drop across my current source?
Negative 80 of the three minus negative 100 of the three.
I disagree. It's just VA. Positive polarity terminal is at the red node. Negative polarity terminal is at ground. So this is the voltage drop. Now, this current, 3Ix, is flowing into the positive polarity terminal. So what do I need to do to calculate my supplied power? Throw a negative sign out front. Another way to think about that would be that the voltage drop across the current source, where we've defined this as the current flowing into the negative polarity terminal. So the positive polarity terminal is at ground. The negative polarity terminal is at this node. So this would be simply negative VA because it's just the voltage at the positive polarity terminal minus the voltage at the negative polarity terminal. Okay. So for those of you with the TI calculators, it actually stores all of that stuff for us automatically. So I could get out of my system solver by pressing clear. I thought I could anyway. Quit. So it's going to store whatever we had for our first variable in as X, our second variable is Y, and our third variable is Z. So I could type in -3 times, so let's see, VA is our first variable. So I'm going to do a fraction here. So let me press the fraction button wherever the hell it is. There we go. So X minus Z for VA minus VC over 10. And then multiply that by another X. And apparently our dependent current source is supplying 160 over 3 watts of power. How much power is supplied by our 2 amp source? Well, I think very obviously the current from the 2 amp source is 2 amps. Okay. I don't think anybody's going to argue with that one too much. What voltage should I put? So it's either going to be VB minus VC or VC minus VB because that current source is between those two nodes. Okay. So we want the current to flow into the negative polarity terminal to calculate supplied power. Okay. So this would mean the minus sign is over here, plus sign is over here. This is the voltage drop across our current source, right? So it flowed into the negative, out the positive. So that would be VB minus VC. Going back to the calculator, 2 times Y minus Z gives me 40 watts. Okay. It should be fairly obvious, but I can use these nodal voltages to find any voltage and any current in this system, even if they're not a nodal voltage, right? So we just found the voltage drop across that current source by saying it's just the voltage at the positive polarity node minus the voltage at the negative polarity node. That would be true if we wanted the voltage drop across the 5 ohm resistor. That would just be VA minus VB. If we wanted positive polarity on top, if we wanted positive polarity on bottom, it would be VB minus VA, right? And then any currents we want through a resistor is just going to be the voltage drop across the resistor in terms of the nodal voltages divided by the resistor value itself. So using the nodal analysis method, we are one step away from figuring out any other quantity we might need. Okay. So if we can find all of those nodal voltages, we can use them to find every other voltage, every current, and every power in our system just by using basic circuit analysis relationships. All right. So now let's break things for a moment by including voltage sources. Okay. So this is going to be our second problem. And let's see here. How can I make this relatively tricky? Let's make this a 3. I actually no. I'm gonna make some changes here. That's gonna be IX. This will be 3VY. Okay. I'm doing this because we're going to wind up needing to use MathCAD for this, and I want to show you that MathCAD can be a bit of a dick sometimes. So I'm switching that to make it give me an error when I do something. All right. So let's say that this will be our current IX. And let's make this voltage across that diagonal VY. All right. So this looks like a pretty damn gross circuit. Okay. So we're going to use the nodal analysis technique here. And I'm just going to tell you straight from the jump that we're going to run into a couple of problems when we hit our voltage source, and we'll talk about how we're going to fix that in a moment. Okay. So we're going to start off by doing everything exactly the same as we did in the previous example, okay? So our first step is going to be to identify our nodes. So we've got this guy here at the top left. This guy here, the top right. We've got a node right here, a node right here, a node right here, and a node down here. Okay. So 1, 2, 3, 4, 5, 6 nodes total. I counted that correctly? Yeah. So 6 nodes. Okay. 6 nodes and 2 controlling variables. So we're going to have to come up with 8 total equations for this system. Okay. For what it's worth, problem 7 of your upcoming homework set, you'll be setting up an 11 equation, 11 unknown system. So this would be considered medium difficulty, even though it looks brutal. All right. So our next step is going to be to assign our reference node, just like it was before. Okay. And I'm going to talk a little bit about this. So in the prior example, when we only had current sources, I said that the best choice for the reference node is usually the node that touches the largest number of circuit elements. Okay. Whenever we have voltage sources, the best choice for our reference node is the node that touches the most voltage sources. Okay. So our red node touches one voltage source, our purple node touches one voltage source, our green node touches one voltage source, and our light blue node touches one voltage source. So any of those is fair game to be ground. Generally speaking, I would tend to put my reference at the negative polarity terminal of a voltage source just because it's going to make the math ever so slightly easier. It's not going to hurt anything if we don't do that, but we're going to eliminate one extra negative sign. And I know that I'm just shit dealing with negative signs. So that's why I would put it at the negative polarity terminal of a voltage source. So does that mean, or I'll let you guys pick between the purple node in kind of the top middle or the light blue node at the bottom? The light blue node at the bottom. You guys are boring. Okay. For what it's worth, you can put your reference node literally anywhere. I'm just trying to give you guys some hints as to what better choices might be that will make your math slightly easier. But technically, you can choose wherever the hell you want it. If you just always want to put it on bottom and just let the chips fall where they may, that's your choice. It can be done. Okay. All right. So we've assigned our reference node. So now we're going to go to step 3, which is to assign our nodal voltages. To all of our non-reference nodes. So I'm going to say that this guy is node A that has some nodal voltage VA. Then we'll have node B with some nodal voltage VB. Here's node C with some nodal voltage VC. Here's node D with a nodal voltage VD. And lastly, here's node E with a nodal voltage VE. Okay. Step number 4 will remain the same as well. So what we're going to do, I don't know why I underlined that one and not any of the others, so I'll get rid of that. is we're going to express our controlling variables in terms of our nodal voltages. So since we have two controlling variables, the current Ix and the voltage Vy, we're going to wind up having two equations here. So let's start with Ix. Can anybody help me out in defining that guy?
VC minus V8 per power.
All right. Anybody have any problem with that? Seems legit to me. The last one is then going to be our controlling variable Vy. So I mentioned this a moment ago when we were defining the voltages drops across current sources and stuff like that. But anytime we're trying to define a voltage in a nodal analysis system, we're just going to say whatever nodal voltage is at the positive polarity terminal minus whatever voltage, nodal voltage is at the negative polarity terminal. So the positive polarity terminal of this voltage Vy is at which node? Purple node. So that means we're going to have Vb minus what's the nodal voltage at the negative polarity terminal? Vc. So for what it's worth, even though I drew this voltage diagonally like a jackass, it's just the voltage drop across the 10 ohm resistor. I drew it in such a way to try to confuse you guys. I will be that kind of asshole on the exams and stuff as well, just so you're aware. Yay. You'll see it on the practice tests and all of that kind of stuff. Okay. So now, so step 5 earlier was to write a KCL expression at each non-reference node, okay? So we're going to try to do that. I'm going to do it over here on the left, and we're going to run into a little bit of a problem if we try to write a KCL equation at node A, okay? So let's see what shakes out of this really quickly, okay? So if we were to try to apply KCL at node A, we would be adding this current flowing up, this current flowing to the right, and this current flowing down together. Well, the current flowing up is just going to be VA minus VC over 5 ohms, right? So that's very easy and well behaved. And the current flowing down is just going to be VA minus VD over 2 ohms. Again, very easy, very well behaved. Now we've got the current flowing to the right through that 8-volt source. Anybody have any thoughts? Let me sweeten the pot. I've got a crisp $100 bill for anybody that can tell me how to do it. Define the current flowing through the 8-volt source in terms of our nodal voltages. I'm very confident that I'm going to keep my money because it's literally impossible. Yeah, it's literally impossible. Sorry, nobody's getting paid for me today. Yeah. So the best that we can do is introduce another variable, okay? So we could call this current flowing from left to right through that voltage source. So I'm going to put this IA 8 volts left to right. Okay. It's still not in terms of the nodal voltages, so I'd still keep my money. So we've introduced another variable into this system. Okay. So that means we now have to come up with another equation somewhere, potentially. Okay. So let's move on to node B. Okay. I'm going to do this one over here. And I think it should be very obvious, but we're going to run into a similar problem. So at node B, I've got my current flowing through my 8-volt source. Again, I've got my current flowing through my 10 ohm resistor, and I've got my current flowing through my 4 ohm resistor. So starting with the things that we can actually define, the current flowing through the 10 ohm resistor would be VB minus VC. Over 10 ohms. Then we'd have VB minus VE over 4 ohms. And then we'd have the current flowing through the 8-volt source from right to left. And again, I'm just going to have to make up another variable here. I 8 volts from right to left and set this equal to 0. So it should be pretty obvious that I 8 volts from left to right is the exact same thing as I 8 volts from right to left, except that it has the opposite sign. Okay. So I'm going to do something a little weird here. And let me explain why I'm allowed to do this, other than the fact that I say I am. The equation that we have here on the left is equal to 0, and the equation that we have on the right is also equal to 0. So I say that I can add these two equations together because 0 plus 0 is still equal to 0. Does anybody have beef with that? So by adding these two equations together, those two currents that are flowing equal but flowing in the opposite directions will wind up canceling each other out, which means I don't have to write an extra equation because I got rid of those variables. Okay. So if I added these together, the result would be VA minus VC over 5 ohms plus VA minus VD over 2 ohms plus VB minus VC over 10 ohms plus VB minus VE over 4 ohms is equal to 0, right? That's the result of me adding those guys together. I'm going to put a pin in this relationship, and I'm going to show you a different and probably better way to get here, okay? So it's based on this same concept, but I'm going to introduce what's called a supernode, okay? So for right now, I'm going to erase all of these arrows. And what I'm going to do is I'm just going to draw a bubble around any voltage source I see. Okay. So I'm going to call this bubble supernode AB because it encloses node A and node B. And for what it's worth, at this voltage source down here, I'm going to have another supernode, excuse me. And so this is going to be supernode D and ground. So I'm going to do that as a lowercase g. So with this concept of a supernode, if I added the currents that are leaving the supernode, this guy, this guy, this guy, and this guy, it's just going to give me those 4 currents added together equal to 0. Okay. So this concept of a supernode is just a shorthand notation for KCL at A, KCL at B, adding those results together, canceling out the opposing currents that flow through the voltage source, we get to skip like 4 steps of doing the same thing and just say, hey, I'm going to get the same result if I just find the currents that are leaving the voltage source. So that's what we're going to do instead. Okay. So I'm going to erase all of this junk down here because it's no longer needed. And I'm going to put step 4 here. Excuse me, step 5. I'm going to leave this blank. We're going to come back to this in just a second. And then down here, I'm going to put step 6. And it will be to apply KCL at all supernodes that do not, I'm going to underline that because it's very important, include the reference node. Okay. We've only got one supernode that does that. So that would be KCL at supernode AB. And I'll be damned if we don't already have that equation. So I'm just going to take this, move it over here so that it lines up a little nicer. Okay. So we've already got step 6 done. Okay. So now let's figure out what the hell that missing step is. Okay. So we've got a little bit of a problem still because supernode AB is 2 nodes and we only got one equation out of it, which means we need to figure out how to get another equation. Okay. So what we're going to do is we're going to write a voltage relationship equation. And we're going to write a voltage relationship equation for every voltage source in our circuit. Okay. So let me just write that down. So write a voltage relationship equation for each voltage source. Okay. So we've got 2 voltage sources in this circuit. So the first one is the 8-volt source. So what's the voltage at the positive polarity terminal of the 8-volt source? I'm at step 5, and I just wrote 8 volts. Okay. So what's the voltage at the positive polarity terminal of the 8-volt source? Or the nodal voltage at the positive polarity terminal of the 8-volt source? Which one's touching the plus sign? VA. Minus the nodal voltage at the negative polarity terminal. So which nodal voltage is touching? All right, VB. So this is one of our 2 voltage relationship equations, defined just like how we've written every other voltage equation doing nodal analysis. So nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. Because I didn't give myself quite enough room, I'm going to do the other voltage relationship equation over here to the right. So what's the nodal voltage at the positive polarity terminal of the 4IX voltage source? What's the nodal voltage at the negative polarity terminal? 0. So I'm just going to leave that part off. So we just have 4IX is equal to VD. Okay. All right. So we've written our voltage relationship equations. For what it's worth, I put that as step 5 so that we remember to do it early. Because that's one of the easiest relationships to forget to write, and you're going to get your system and be like, well, shit, I don't have enough equations to solve for this. So I put the equations that are easiest to forget to write first to remind you, hey, do these first and then do the KCL at the end to make sure that you have enough equations. You can choose to do anything past step three in whatever order you feel like. But if you come to me asking for help, I'm going to say, did you do the steps in the order I told you to? And if you didn't, I'm going to make you redo the problem in the order I told you to, just as a heads up, because this is the correct way. I'm arrogant enough to say that. All right. So step number 7 is going to be to write a KCL equation at all remaining non-reference nodes. So for us, that would just be node C and node E, because A and B already has a KCL equation. Supernode DG will not get a KCL equation because it is a supernode that contains ground. So we move along from that one. So we just have KCL at node C and KCL at node E to write. So at node C, we're going to have this current, this current, this current, and this current. So somebody just start me off.
VC minus VA over 5.
VC minus VA over 5. Thank you, Micah. So that's the current flowing up. All right, somebody give me another term.
VC minus VB over 10.
Okay, VC minus VB over 10. Somebody give me another term.
VB over 8.
VC over 8. All right. So that's the one flowing down. So lastly, we have the current flowing through the dependent source, which it seems like you guys are avoiding. I don't understand it. It's the easiest one to write. 3VY. Now we'll do KCL at node E. So that's going to be this current, and this current added together. So somebody start me off with this one as well, please. Negative 2 amps. All right. Negative 3 VY. VB minus, sorry, VE minus VB over 4. Yeah, I misheard you. All right. So let's count things up here really quickly, okay? So we've got one equation, two equations. Here's number 3. Here's number 4, 5, 6, 7. Okay. So I have 5 nodal voltages to solve for, and then 2 controlling variables. So that's 5 plus 2 is 7. So 7 equations, 7 unknowns. I'm done. Okay. Now, there's no way in hell I'm going to try to simplify this down to be able to put it in my calculator. Okay. So instead, I'm going to use MathCAD and use the solve block in order to handle all of this math for me. Yes. How many nodal voltages do you have? Not so every node except for the reference will give you one equation, and then however many controlling variables you have. All right, so I'm opening up my son of a bitch. I may have forgotten to reinstall MathCAD. on my computer. Um, Damn it. Okay. You guys are going to work on the ICA for a little bit while I reinstall MathCAD on my computer. And then we'll circle back around to this. Sorry about that. You just fucking do it. That's from the last class meeting. All right, MathCAD installed faster than I thought it would. That's great. So let's get to it. Okay, so to use the solve block, which is what we're going to use to solve this system of equations, it does require a paid license for MathCAD, which you guys all have access to because you're Louisiana Tech students. So don't know how many of you have paid attention to this. Perhaps some of you, perhaps none of you. But if you go to our Canvas page, I'm going to feel like a real jackass if I didn't do this, but I'm 99% sure that I did. Yep. There's a thing down here on the introduction section that says MathCAD Prime 9.0 download and instructions. If you click on this, it sends you to the software page on the Living with the Lab website, which your credentials should still get you into. This is the license server that you should use. This is the port that you should use when you set up the MathCAD, and then you'll be connected to Louisiana Tech's license server, which means you can use this wherever you want. All that kind of good stuff. Okay. In the spring quarter, just for what it's worth, is when the university renews our license. So you might see for a couple of days, it might say like 28 days remaining or something on your license. That's going to go away. It's handled by the college, so you don't need to worry about it. Only if it hits 0 days should you panic. Okay. Okay. So we're going to set up a solve block here. So I'm just going to click somewhere in this field and press this solve block button. And the solve block is divided into 3 distinct parts, okay? So there's a part that says guess values, there's a part that says constraints, and there's a part that says solver. So we're going to start in the guess values, okay? So we have to essentially declare variables that we're trying to solve for, okay? And we have to give the computer a place to start from because it is an iterative solver. So it runs it hundreds of times or whatever, trying to get to some final solution that satisfies all of the constraint equations that we give it, but we have to tell it what our starting value is. I usually just set all of my variables to have a starting value of 1. So if it's a voltage, it's 1 volt. If it's a current, it's 1 amp. Okay. So we had 5 nodal voltages. So VA, VB, VC, VD, and VE. So I'm going to start on those. So here's VA, and I'm going to do shift colon 1 volt. And so that's me saying, hey, there's some variable VA that I'm solving for, and I'm going to guess that its initial value is 1 volt. Then I'll do VB is 1 volt, VC is 1 volt, VD is 1 volt, and VE is 1 volt. Okay. Then I have those 2 controlling variables, right? So I had a current IX, so I'm going to set that guy to be 1 amp. And I had the controlling variable Vy. Since that's a voltage, I'm going to do that as 1 volt. Okay. So those are my 7 variables. I've declared them all. Okay. So now I'm getting into the constraints section. So in the constraints section, this is where we're going to type in the equations that we came up with, all 7 of them. Okay. So I'm just going to go through these one by one. So I'm going to start with this guy right here for Ix. So we have Ix is equal to Vc minus Va over 5 ohms. So I'm going to type in Ix. And since this is a constraint equation, I'm going to use a different equal sign here. I'm going to press Control equals, and it's going to give me this boldface equal sign. Then I believe it was Vc minus Va over 5. To get ohms, I'm going to do Shift W. Shit, I had my cursor in the wrong place. Shift W and then Control G. If you can't remember Shift W and then Control G, that's fine. You can go into this symbol menu here, and it has all the lowercase Greek letters and the uppercase Greek letters. It also has the keyboard shortcut where it has capital W and then Control G. So for what it's worth, Control G just converts whatever previous character into Greek. So, all right. So this boldface equal sign essentially means force whatever's on the left-hand side to be equal to whatever's on the right-hand side. So these are the equations that we want to use to solve our system. So I'm using that particular equal sign. I'm going to go over here to the right a little bit. I'm going to put the next equation in. So that was Vy is going to be equal to Vb minus Vc. So Vy is control equals to Vb minus Vc. Now I'm going to be in my voltage relationship equations. So the first one is going to be 8 volts is equal to Va minus Vb. And then I had 4 Iy, I think. 4 Ix is equal to Vd. Okay. If I can find my damn cursor. All right, I'm just going to Alt Tab. For what it's worth, I have intentionally made a small mistake here. It is not remotely obvious, so we'll sort that out in a moment. But I want MathCAD to give me a very specific error because you guys are going to see it relatively regularly. And so I want to make sure that you know what it means. Now I'm going to go on to my other constraint equation. So this is going to be where I'm going to start my KCL at supernode AB. So let me scroll up here. So VA minus VC over 5 ohms. VA minus VD over 2 ohms. And by the way, if anybody has any questions about what I'm typing or wants me to slow down or anything, just let me know. VB minus VC over 10. and VB minus VE over 4. I'm going to set this equal to 0, and I'm just going to move this down a smidge. All right, and now down here, I'm going to write my KCL at node C equation. So VC minus VA over 5. VC minus VB over 10. VC over 8, and then 3VY. And now I'm going to do my KCL at node E. So that was, I think, negative 2 amps. Let me double check. Yep, negative 2 amps minus 3VY. Plus VE minus VB over 4 ohms, control equal to 0. So 1, 2, 3, 4, 5, 6, 7 equations. So I have all of them typed in. I'm going to scroll down here. I'm going to make this part a little bit larger. So what I'm about to do is technically optional. That being said, I think you should do it 100% of the time. Okay. I'm going to put a matrix here. And since I have 7 variables, I'm going to do this as a 7x1 matrix. I'm just going to move this down. And I'm just going to type all of my variables into this matrix. So VA, VB, VC, VD, VE, IX, and VY. And then I'm going to do shift colon for that equal sign that we used up above in the guess values section. And I'm going to type find. I think it doesn't matter if you do uppercase F or lowercase f. I'm just in the habit of doing uppercase F. And then I'm going to type in all those variables again, separated by commas. So I'll have VA, comma, VB, comma, VC, comma, VD, VE, IX, and VY. And for what it's worth, I want these variables written in the same order as I put in that column, because what's happening is it's going to find the value of these and store them in that matrix. Okay. So I want to put them in the same order so that, we get apples to apples kind of thing here. Finally, over here on the far right-hand side, I'm going to press just a normal equal sign, and I'm expecting an error. Okay. So I don't know if you guys can read this because that screen's a little bit blurry, but it says these units are not compatible. Okay. And the reason it's saying these units are not compatible is because of our dependent sources. Okay. So if we look back at our circuit diagram here, this 4ix voltage source is a current controlled voltage source. Okay. So what should the units on that scaling factor of 4 actually be? Volts per amp. Okay. So if I go back in here, and here where I see 4ix, I'm going to highlight the 4, put a parentheses around it, and then I'm just going to give it units of volts per amp. This should make better sense now, right? So 4 volts per amp times some current is going to give us a voltage. So we fixed that one, okay? Well, at 3VY, that was a voltage controlled current source. So what should the units on that 3 be? Amps per volt. Yep. So everywhere I see 3VY, I'm going to highlight that 3 to amps per volt there. Same thing here. And if I fixed all of those, and I believe I have, it should spit out numbers. Yay. One thing that is important, so I'm going to explicitly say this so that it will be recorded. If we declare 7 variables at the beginning, up here in the guess values section, we have to find 7 variables down here, okay? If we don't, it's just going to use whatever information happened to be in that register of your computer's memory and just come up with some random bullshit, okay? So if we declare 7 variables, we have to write 7 equations and solve for 7 variables. Otherwise, what MathCAD gives us will have errors in it. Okay. All right. Now I'm done, unless anybody has any questions.